Tonight, we're going to explore one of the most unsettling paradoxes in our cosmic neighborhood. If you ask most people which world would be harder to survive on, the answer would almost always be Mars. It's farther away, colder, more isolated, more alien. So it seems obvious that Mars must also be the deadlier destination. But it isn't. The most dangerous place humans are seriously planning to visit isn't millions of kilometers from Earth. It's the world that's been hanging over our heads every night for as long as our species has existed. The Moon. The place we reached more than half a century ago. The place we're preparing to return to. The place many people see as the easiest step toward becoming a spacefaring civilization. And yet, in almost every way that matters to the human body, the Moon is less forgiving than Mars. By the end of tonight, you'll understand why the Moon's vacuum, extreme temperatures, abrasive dust, and relentless radiation make it one of the harshest environments humans have ever attempted to survive, why Mars is surprisingly more forgiving in several crucial ways, and why the Moon's brutality is exactly what makes it the proving ground we cannot afford to skip. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The Moon is 3 days away. That is the distance. 3 days by spacecraft. About 384,000 kilometers. Roughly 1 light second if you measure in the language of physics. Cosmically, it is practically next door. Humans landed there in 1969, more than half a century ago, and agencies still treat it as a stepping stone, a first foothold before the longer reaches. The closeness feels reassuring. It should not. Proximity has nothing to do with hospitality. Step onto the lunar surface without a suit, and you have roughly 15 seconds of useful consciousness. Not 15 minutes, not 5 minutes, 15 seconds. After that, you are unconscious, dead in under 2 minutes. Most people picture explosive decompression when they imagine this. The image from dozens of films, bodies rupturing in a vacuum, that is a movie myth. The real mechanism is quieter and more final. When there is no atmospheric pressure surrounding you, the only oxygen reaching your brain is what is already dissolved in your blood. That supply lasts about 15 seconds. Meanwhile, the fluids in your body, the liquid in your lungs, your sinuses, the moisture in your tissues begin to vaporize. Not because the vacuum is hot, because without pressure, liquid cannot stay liquid at body temperature. It does not boil in the dramatic sense, it simply changes state. And you do not freeze instantly either, because in a vacuum, there is no air to carry heat away by conduction. Heat leaves slowly, by radiation alone, so you are not frozen and you are not exploded. You are simply gone. 15 seconds, 2 minutes. The suit is not gear in the way a helmet is gear or a jacket is gear. The suit is the only thing between you and that. But suppose you are a trained astronaut with the best equipment ever built. Suppose the suit holds. The Moon still has a list of other problems, and the next one is a design nightmare that even the best suit cannot simply solve. Think about what sunlight means on the Moon. There is no atmosphere to filter it, no cloud cover to moderate it, no weather system to interrupt it. When sunlight hits the lunar surface, it hits directly and completely. The temperature climbs to about 127 degrees Celsius. That is above the boiling point of water. Hot enough to melt certain materials, hot enough to fuse surfaces that were never meant to touch, hot enough to cook. Now think about how long that lasts. A single lunar day is about 27 Earth days. That means roughly 2 weeks of continuous, unfiltered, blazing sunlight. Not a day of sun followed by a night of cool. 2 weeks. The same patch of ground baking without interruption. And then the sun sets. Temperature drops to about minus 173 degrees Celsius, which is roughly minus 279 degrees Fahrenheit. Colder than most of Antarctica by a margin that is hard to picture. The darkest, coldest places on Earth do not approach this. The most extreme temperature swings recorded anywhere on our planet. The Sahara against the depths of a Siberian winter do not come close. The swing between lunar day and lunar night is about 300 degrees Celsius. In about 2 weeks, a surface goes from hotter than boiling water to colder than any place most humans have ever experienced. Then it reverses. Then it reverses again. Think about what that does to materials. Every solid material expands when it is heated and contracts when it is cooled. That is basic physics. A bolt expands in the heat and contracts in the cold. A seal does the same. A circuit board, a structural joint, a habitat wall. On Earth, engineers design for thermal cycling, but the ranges they plan around are modest. Even in demanding environments, the swings are manageable. A 300-degree swing over 2 weeks is a different problem entirely. Every component must survive that cycle, then survive it again, then again, for months or years of habitation. A failure in a seal, a fracture in a structural element, a short in an electrical connection, any of those can be fatal on a world with no air and no rescue within 3 days. The moon is a design nightmare. That is not a loose phrase, it is an engineering verdict. Here's where it gets strange, because you might expect Mars to be worse. Mars is cold. Its surface averages about minus 60 degrees Celsius, and near the poles in winter, it reaches about minus 125 degrees Celsius. Those are serious numbers, but a Martian day lasts 24 hours and 40 minutes, almost identical to an Earth day. And Mars has an atmosphere, thin as it is, about 1% of Earth's atmospheric density at the surface. That is almost nothing. But almost nothing is not nothing. That thin envelope of gas still acts as a slight thermal buffer. It moderates the extremes. Mars does not swing from scorching to frozen over the course of weeks. Its temperatures are cold, but they are relatively steady. They are a problem engineering already knows how to address. Mars gives a fighting chance. The moon does not in thermal terms. This is the first place the comparison reveals itself clearly. The moon is cosmically close. Mars is cosmically distant. And yet, for the task of keeping machines and people alive over long durations, Mars's cold consistency is more forgiving than the moon's violent thermal rhythm. Closer does not mean friendlier. The moon keeps proving that. But temperature is not even the most dangerous thing the lunar environment offers. The real threat is invisible. You cannot see it, cannot feel it, cannot detect it without instruments. And when we get there, it will put the moon's thin excuse for an atmosphere, and Mars's thin but real one, in a very different light. Radiation is that threat. It is not the radiation you encounter at a dentist's office, not the low-level background hum of ordinary life. This is something older and more relentless. It has been streaming across the universe since the first stars exploded. It crosses billions of light years without slowing, and right now, 2 invisible shields are blocking most of it from reaching you. Remove those shields, and you get the moon. The first source is the sun. Our star constantly sheds a stream of charged particles, mostly protons and electrons, that races outward in every direction. Under normal conditions, this solar wind is a steady, manageable pressure. But the sun is not always calm. It erupts. Solar flares and coronal mass ejections, eruptions of plasma and magnetic energy from the sun's surface, can spike radiation levels dramatically in a matter of hours. A solar particle event of serious magnitude, caught outside a habitat, without proper shielding, can deliver doses that cause acute radiation sickness, nausea, vomiting, hair loss, immune collapse, in extreme cases, death. And the warning time is measured in hours, not days. The second source is slower to understand, but harder to stop. Galactic cosmic rays are among the most energetic particles in existence. They were born in the violent deaths of stars, supernovae, neutron star collisions, the turbulent environments around black holes. These particles travel at near light speed. They are essentially bare atomic nuclei, stripped of their electrons, so fast and so energetic that they can punch straight through several centimeters of solid metal. They do not slow at an aluminum wall. They pass through it. Scientists have taken to saying, with a precision that sounds almost like dark humor, that galactic cosmic rays laugh at aluminum walls. That phrase is not an exaggeration. It is the engineering problem. So why is life on Earth's surface possible at all? 2 reasons, and most people have never thought about either one. The first is the magnetosphere. Earth's core is churning molten iron, and that motion generates a vast magnetic field that surrounds the planet like a bubble. The magnetosphere deflects the solar wind and redirects much of the incoming cosmic radiation. It does this silently, invisibly, constantly, every second of every day. The second is the atmosphere. There is roughly 10 metric tons of air above every square meter of the ground you are standing on. That mass of gas absorbs and scatters incoming particles before they reach you. Together, these two shields make Earth's surface one of the most radiation-sheltered environments in the inner solar system. The baseline dose on Earth's surface is about 3 millisieverts per year. That is the number your body is built around. Now, step off the planet. The International Space Station orbits in low Earth orbit, still partly inside the magnetosphere's protection. Astronauts there absorb roughly 240 millisieverts per year. That is about 80 times the Earth's surface baseline. NASA tracks cumulative lifetime dose for every astronaut and imposes career limits because of it. 80 times the baseline, with the magnetosphere still partly in effect, is enough to require career management. Now remove the magnetosphere entirely. Remove the atmosphere. Stand on the moon. European Space Agency research puts the lunar surface dose at up to 700 times Earth's baseline. Not 80 times, 700. Physicist Marco Durante has made the point plainly. One single day in space beyond Earth's protection can equal an entire year's worth of Earth's surface radiation. One day. And a lunar mission is not one day. The biological consequences are serious at every level. High-energy particles tear through DNA like bullets through paper, breaking strands, causing mutations, raising the lifetime risk of cancer with every hour of accumulated exposure. NASA's twin study examined this directly. Scott Kelly spent nearly a year aboard the International Space Station, while his identical twin, Mark Kelly, remained on Earth. When Scott returned, researchers found radiation-linked changes in gene expression, measurable immune disruption, and DNA damage. That was with the partial protection of low Earth orbit. On the moon, those effects would be stronger. But there was more to the story. Cancer risk is not even the full picture. Particle accelerator studies that simulate the space radiation environment have found evidence that cosmic rays can damage the brain and central nervous system. Animal models show signs of cognitive decline, memory problems, impaired decision-making. The research is still developing, still working from animal data toward human conclusions. We do not yet know the full scale of the effect in humans, but the pattern in the evidence is consistent enough that it sits near the top of NASA's list of unsolved health challenges for deep space exploration. Scientists writing in the journal Science in early 2026 called radiation the showstopper, the number one limitation on how far and how long humans can safely explore deep space. On the moon, with no natural protection at all, it is the defining problem of any long-duration mission. The engineering response has been real, but partial. Current shielding absorbs lower energy solar particles reasonably well. For solar particle events, getting inside a reinforced habitat fast is meaningful protection. NASA's Orion spacecraft, flying on Artemis II, the first crewed flight beyond the magnetosphere since Apollo 17 in 1972, includes a designated storm shelter beneath the cabin floor, padded with stored equipment for extra mass. In 2022, Artemis Award flew 2 radiation-sensing mannequins, named Helga and Zohar, to gather precise data. One of them wore a protective vest from Israeli company Stemrad. The results suggested the vest reduced solar storm exposure by roughly 40 to 60%. That is meaningful progress. But 40 to 60% of a potentially lethal solar storm dose is still significant. And the vest does nothing against galactic cosmic rays, which pass through it the same way they pass through aluminum walls. And there is one more layer the moon adds that most people do not expect. High-energy particles slamming into the lunar soil do not simply stop. They trigger cascades of secondary particles, neutrons, and gamma rays that scatter outward in all directions, including upward. The surface itself becomes a source of radiation. China's Chang'e 4 lander, which reached the far side of the moon in 2019, carried an instrument called the Lunar Lander Neutrons and dosimetry experiment, specifically to measure this. The data confirmed it. On the moon, you are not simply being irradiated from above. You are being bombarded from the sides and from below. The ground itself is radiating back at you. A simple roof is not enough. Now consider Mars. Mars has no global magnetic field. Its field collapsed billions of years ago, leaving only weak, patchy remnants in the crust. By that logic, Mars should be as exposed as the moon. But it is not. Not quite. Its atmosphere, thin as it is, about 1% of Earth's density, mostly carbon dioxide, still does something. It stops some particles. It slows others. It causes incoming radiation to interact and fragment before reaching the surface. NASA's Curiosity rover has been measuring this directly since 2012, using its radiation assessment detector. The result? The Martian surface receives roughly 233 millisieverts per year. That is serious. It is well above Earth's baseline, but it is dramatically lower than the unprotected lunar surface. The atmosphere is doing real work, and architecturally that first layer matters. On Mars, a habitat reinforced with piled Martian soil can bring surface doses toward manageable ranges. The atmosphere provides the outer filter. The habitat design provides the inner one. You have two layers to work with. On the Moon, you start from zero. Every bit of shielding must be built or brought, and for galactic cosmic rays, no shielding both effective and light enough to be practical yet exists. That problem is open. It is not solved. There is something worth pausing on, briefly, before moving forward. The carbon in your DNA, the iron in your blood, the calcium in your bones, all of it was forged in stars that died billions of years before the solar system formed. You are made of stardust. And the radiation streaming through the lunar surface right now is the legacy of those same stellar deaths. The galactic cosmic rays tearing through aluminum walls were born in supernovae, in the same violent processes that built the atoms you are made of. We are, in a real sense, the universe becoming aware of itself, and we are running headlong into the raw energy that created us. The cosmos does not consider that ironic, but the radiation is the hardest problem between us and a sustained presence beyond Earth. And the Moon sits at the unprotected end of that problem. Mars, by accident of its atmosphere, sits somewhere less severe. The difference is not safety, it is margin. And on a world where everything is trying to kill you, margin is everything. The radiation problem alone could end a mission before it truly begins. But radiation is not the only resource the Moon fails to provide. Radiation is not the only thing the Moon fails to protect you from. The next threat sounds almost trivial by comparison. It is the kind of thing you brush off a shelf without thinking. You sweep it into a corner. You wipe it from a windowsill. Dust. And yet the astronauts who walked on the Moon came back cursing it more than almost anything else. Here is what most people picture when they hear the word dust. Something soft, something powdery, desert grit worn smooth by wind, volcanic ash rounded by water. Even the finest household dust has been tumbled and abraded by air currents, by humidity, by contact with other surfaces over time. Earth's materials are shaped by billions of years of weathering. Their edges are worn down, their surfaces are dulled. The Moon has no wind, it has no water, it has no rain, no rivers, no ocean waves. It has nothing that rounds an edge or smooths a grain. What it has instead is billions of years of constant bombardment. Micrometeorites striking at enormous speed, cosmic rays threading through the surface, solar wind particles sandblasting exposed rock at the atomic scale. This process grinds lunar rock into ever finer fragments, but it does not smooth them. It shatters them. It melts them. It fuses them into strange, irregular shapes. Under an electron microscope, lunar dust grains look almost menacing, jagged, angular, glassy. Many are partially melted and re-solidified by the heat of micrometeorite impacts, forming sharp, irregular geometries. Some are hollow spheres of ancient volcanic glass. Some have edges finer than industrial cutting surfaces. The dust that coats the Moon is not soft. It is a collection of microscopic razors, and with no atmosphere to create electrostatic equilibrium, those razors carry powerful charges. They cling to everything they touch with a tenacity that felt, to the astronauts, almost aggressive, almost deliberate. Buzz Aldrin called it one of the most persistent, annoying problems of the entire mission. Neil Armstrong noted that dust coated every surface within minutes of the first moonwalk. Suits were visibly darkened. Brushing did nothing. The dust clung to suits, gloves, equipment, and visors with enough force that it could not simply be wiped away. It scratched visors, permanently reducing visibility. It worked its way into suit joints, grinding the mechanisms and degrading the suit's ability to flex and seal. Pete Conrad, who walked on the moon during Apollo 12, compared the abrasiveness to fine sandpaper that never goes away. Not sandpaper you finish with and set aside. Sandpaper working continuously, every time you move. Then the suits were repressurized inside the lunar module, and the dust came in with the astronauts. Harrison Schmitt, the only professional geologist to walk on the moon and part of the Apollo 17 crew, almost immediately noticed watering eyes and congested sinuses. He described the disturbed dust as smelling like gunpowder or spent fireworks. Several others reported similar reactions. What they were sensing was chemical reactivity. These particles had never been exposed to oxygen or water. Their surfaces were primed to react with the first biological tissues they contacted. Fresh, sharp, chemically hungry. But the respiratory irritation in the cabin was the mildest version of the problem. The deeper problem is what happens when those particles travel further in. Particle size determines where dust ends up in the human respiratory system. Particles larger than roughly 10 micrometers are caught by the nose and upper airways. They irritate, but the body's defenses handle them reasonably well. Particles between 2.5 and 10 micrometers reach deeper into the airways. And particles smaller than 2.5 micrometers, what air quality scientists call fine particulate matter, penetrate all the way to the alveoli. The alveoli are the tiny air sacs where oxygen crosses into the bloodstream. The body's ability to clear particles from this region is dramatically reduced. Particles that reach the alveoli tend to stay there. Lunar dust spans every one of these size ranges. A significant fraction sits in the deepest, most dangerous category. And unlike rounded terrestrial dust, these particles are coated in chemically active compounds. Nanophase iron, agglutinates, glassy materials, all of them especially good at generating free radicals in biological fluids. Free radicals are unstable molecules. They damage cells. They tear DNA. They trigger inflammation that the body cannot always resolve. The analogy to existing respiratory diseases is not reassuring. Long-term exposure to fine silica particles, chemically similar to lunar regolith in some respects, causes silicosis, chronic inflammation, irreversible scarring, progressive fibrosis of the lung. Coal miners' black lung works on the same basic principle. Fine particles lodge where the body cannot clear them, and the body's attempt to deal with them causes more damage than the particles alone. NASA laboratory studies using simulated lunar regolith found that even low concentrations cause measurable cell death and DNA damage in lung tissue cultures. A 2018 study published in the journal GeoHealth found simulated lunar dust to be cytotoxic at levels well below what astronauts might actually encounter during extended surface operations. The answer was stranger than expected. No one actually knows what prolonged lunar dust exposure does to human lungs, because no human has ever stayed long enough to find out. The longest human stay on the lunar surface was Apollo 17, just under 75 hours across 3 moonwalks, roughly 3 days. Even across that relatively brief period, dust caused suit degradation, equipment problems, and the kind of respiratory irritation Schmitt and others reported. What 6 months of daily lunar operations would do to human lungs is not a matter of cautious projection. It is genuinely unknown. There is no data. No one has been there long enough to generate it. The lab evidence is not reassuring, but the lab is not the surface. We do not fully understand what sustained exposure would produce. That open question is one of the reasons the dust problem keeps specialists up at night. But even setting aside what it does to lungs, what it does to machines is alarming enough. During Apollo, dust infiltrated suit joints and bearings, raising the force required to move the suit and accelerating wear on mechanisms designed to flex smoothly. It coated solar panels on surface instruments, cutting power output. Later robotic missions confirmed that dust accumulation on panels was fast enough to become a primary operational concern. The Lunar Reconnaissance Orbiter, which has been circling the moon since 2009, carries dust detection instruments, partly because dust behavior is considered a critical unknown for any future surface presence. And then there is the problem you cannot solve by sealing anything. Constant solar wind bombardment and ultraviolet radiation charge the lunar surface. The effect is especially strong at the boundary between sunlit and shadowed regions. Fine particles lift off. They float, sometimes to several meters or higher. Later Apollo astronauts reported a strange glow along the lunar horizon, just before sunrise, a light that should not have been there. Scientists now believe it was vast clouds of electrostatically levitated dust catching the first edge of sunlight and scattering it across the horizon. The dust was not just on the surface, it was in the air, if air is even the right word for it, carried upward by charge rather than wind. This is the part that collapses the simple engineering solution. You cannot just seal a habitat. Every airlock cycle, every entry and exit, every time a suited astronaut crosses the threshold, dust finds a way in. It clings to suit surfaces. It floats onto equipment that was never physically contacted. Managing contamination is not a problem you solve once. It is a constant daily drain on time, energy, and resources with no clear endpoint. Mars has dust too. Its storms are not a minor footnote. Regional dust storms sweep across Mars regularly, and roughly every few Martian years, a global storm can blanket the entire planet for weeks. In 2018, one of those global storms ended the Opportunity rover mission after nearly 15 years of operation, slowly starving its solar panels of light until the rover went silent. Martian dust is real. Martian dust is a genuine operational challenge. But Martian dust is fundamentally different in character. It has been shaped by billions of years of wind, tumbled and rounded across vast distances, altered by ancient water ice and the thin present atmosphere. It is less angular, less glassy, less chemically reactive, less ready to tear through tissue. Mars soil contains perchlorates, chlorine-containing salts that are toxic to the thyroid in quantity, and that is a genuine colonist concern that researchers take seriously. But perchlorates are water-soluble. They are potentially manageable by filtration and decontamination in ways the purely physical damage from jagged lunar silicates is not. And the electrostatic levitation problem that makes lunar dust inescapable is far less severe on Mars, buffered by even that thin slice of atmosphere and different surface charging dynamics. Dust protocols on Mars would still matter. Suit degradation, respiratory risk, and equipment contamination all require engineering attention, but they look meaningfully more manageable than the same challenges on the Moon. And that closes a pattern. Radiation, temperature, dust. In every category, Mars has a version of the hazard. In almost every category, Mars's version is less extreme, more addressable, or at least within reach of realistically imaginable technology and medicine. The Moon's versions sit at or beyond the edge of what current engineering and current medical knowledge can fully answer for long-duration missions. The comparison is not between a friendly world and a hostile one. It is between two hostile worlds, one of which keeps giving us a little more margin. But these three hazards only capture the physical environment. What a human body endures on the Moon or Mars goes beyond what the world throws at it from the outside. Some of the hardest problems come from within. Every threat covered so far has been something the Moon does to you. Radiation tears through DNA. Temperature swings destroy materials. Dust infiltrates every joint and surface and airway. Each hazard is an attack, something arriving from the environment to damage a body or a machine. Gravity is different. It is not what the Moon does to you. It is what the Moon fails to give you. The human body is not a neutral piece of biology that works identically anywhere. It is an organism shaped by one specific force across hundreds of millions of years of evolutionary history, tuned to one specific number, 1G, one full unit of Earth's gravitational pull. Every bone in your skeleton is dense enough to carry that load and no more. Every muscle in your body is calibrated to move against that resistance. Your heart is sized to pump blood upward against that pull. Your vestibular system, the intricate balance machinery in your inner ear, was built for exactly this field. You are not just adapted to Earth, you are Earth, in a biological sense. And the moment you leave it, the body starts receiving a signal it was never built to process. We know what that signal produces. Astronauts on the International Space Station live in near weightlessness, and their bodies document the cascade with uncomfortable precision. Bone density decreases. Without gravitational load, the skeleton has no reason to maintain its mass, and it sheds mineral content at a rate that would be alarming in an elderly patient on Earth. Muscle tissue follows the same logic, atrophying without constant resistance to push against. The spine lengthens as the intervertebral discs decompress, freed from the compression they normally carry. Fluid that gravity ordinarily pools in the lower body shifts upward toward the head, raising pressure inside the skull. That pressure has consequences for the eyes. A significant fraction of astronauts who spend months in orbit return with measurable changes to their vision and to the shape of the optic nerve, the result of sustained elevated intracranial pressure. Scientists call this spaceflight-associated neuroocular syndrome, or SANS. It is not a minor side effect. In some astronauts, the changes appear to be long-term. Here is the reassuring part, or what seems like the reassuring part. The Moon has gravity. Mars has gravity. Neither world is the orbital weightlessness of the ISS. And that is true. Any gravity is better than none. Partial gravity loads the skeleton, at least partially. Stresses the muscles, at least partially. Makes the heart work at least partially against a downward pull. ISS exercise protocols, the 2 hours of daily physical activity astronauts are required to perform to slow the deterioration, would help on both surfaces too. So the problem is smaller. The question is whether it is small enough. On the Moon, the surface gravity is roughly 1/6 of Earth's. 1/6. That number sounds like it should be meaningful. It is not nothing. But think about what 1/6 actually means for a body built around 1. Bone density loss, muscle atrophy, fluid shift, cardiovascular deconditioning, all of these processes respond to loading. The less load, the faster and more completely they proceed. 1/6 gravity provides some load, probably not enough. The honest scientific position is that we do not know precisely where the threshold is, the minimum gravitational pull that prevents long-term physiological deterioration in a healthy human body. We have not had the ability to test partial gravity in a controlled, long-duration setting, but 1/6 g is, by most assessments, likely below it. Not meaningfully below, likely well below. Mars's gravity is roughly 38% of Earth's. 38% does not sound dramatically better than 1/6. The picture did not hold. 38% is more than 6 times stronger than the Moon's surface gravity. More than 6 times more load on the skeleton. More than 6 times more resistance for the muscles. More than 6 times more work for the cardiovascular system. The difference between 1/6 g and 38% g is not a minor variation in an otherwise similar environment. It is a physiologically significant gap. Over the length of a year-long Mars mission, that gap would accumulate across every single system in the body, every single day. For a short mission, the distinction matters but can be managed. Exercise, medication, careful monitoring, post-mission rehabilitation. These are real tools and they work to a degree. The problem is not the 6-month mission, the problem is the permanent settlement. Think about what it means to live an entire life on another world. Not a mission, not a rotation, a life. People who are born there, children who grow up there, skeletons formed from infancy under that gravitational field, muscles, hearts, eyes, vestibular systems, all of it shaped not by Earth's 1g, but by whatever the world provides. A child born and raised on the Moon would develop under 1/6 g from the first moment of life. Their skeleton would not build the density that Earth children build, because the load demanding that density would never be there. Their muscles would grow to meet the resistance available, which is a fraction of what an Earth body expects. Their cardiovascular system would never learn to push blood against a full gravitational column. And then the question arrives, quietly, and it is a serious one. Could that person ever come to Earth? Not whether it would be uncomfortable. Whether their body, built for 1/6 g, could survive the sudden imposition of full Earth gravity for any extended period. Whether a heart shaped for the Moon could sustain the load. Whether bones calibrated for minimal stress could carry a body that now weighs 6 times what it did at home. We do not know the answer. That is the honest position. The question has not been tested because it cannot yet be tested. But it is not a theoretical concern. It is the kind of concern that shapes how seriously scientists and engineers take the difference between these two worlds when imagining long-term habitation. A child born on Mars faces a similar question. 38% G is still not 1G. The same directional risks apply. Bone density lower than an Earth child's. Muscle mass calibrated to a lighter world. A cardiovascular system that has never fought a full gravitational column. A visit to Earth would be physiologically demanding, perhaps extremely so, but 38% is meaningfully more than 1/6. The body would carry more load from the first breath. The skeleton would face more resistance every time the child stands, walks, runs. The divergence from Earth's baseline would be real, but smaller. We are organisms fine-tuned for 1G. Every fraction of gravitational acceleration matters for the systems that run on loading. The moon offers so little of it that the long-term physiological consequences remain genuinely open, and probably alarming. Mars offers more than 6 times as much, which does not solve the problem but changes its scale entirely. Gravity is the hazard no suit can address, no habitat can filter, no exercise protocol can fully replace. And for anyone imagining not a mission but a civilization, the difference between 1/6 and 38% may be the difference between bodies that can still choose to come home and bodies that cannot. But gravity is not the last internal challenge these worlds would impose. Every system weighed so far is physical. Bone, blood, tissue. The body absorbs radiation, loses calcium, breathes abrasive dust. But there is another passenger on this journey that no radiation countermeasures and no gravity scale can register. The brain. The thing that makes you you. The thing that processes experience, reads danger, holds a crew together under pressure, makes 10,000 small decisions across a mission that each need to be right. The body's hazards have been studied for decades. The minds are only beginning to be understood. Humans are not solitary animals. This is not a preference. It is a biological fact built over millions of years of evolution in groups. We are wired at a deep level for connection, reading faces, hearing familiar voices, the background hum of being near other people, a stranger's conversation across a room, the sound of a city outside a window. These things are not luxuries. They are inputs the social brain expects, and when they disappear, the consequences are measurable and serious. Research on extended isolation does not paint a gentle picture. Anxiety climbs, depression sets in, cognitive performance degrades. In extreme cases, people in prolonged solitary confinement report hallucinations. The reason solitary confinement is widely considered a form of torture is not rhetorical, it is physiological. The brain, cut off from the social environment it evolved to operate inside, begins to fail. Space missions are not solitary confinement. Crews travel together. Communication with Earth is maintained. But here is where the comparison becomes important rather than reassuring. A crew traveling to Mars is not isolated from one other person. They are isolated from almost everyone they have ever known. Family, friends, casual daily interactions, the colleague at the next desk, the server at the restaurant they go to on Sundays. All of it sealed away behind a distance that grows to hundreds of millions of miles. The small group inside the spacecraft becomes, for months or years, the entirety of the social world. The same faces, the same voices, the same confined space, day after day, with nowhere else to go. NASA has studied this seriously. The method is analog research, isolated Antarctic research stations, underwater habitats, sealed simulation facilities where small crews live in tight quarters for weeks to months, without access to the outside world. The findings have been consistent enough to give the phenomenon a name: the third quarter effect. It works like this. The early weeks of an isolated mission bring energy and novelty. The crew is alert, motivated, engaged with the challenge. Around the midpoint, something shifts. Morale dips. Irritability rises. Interpersonal tensions that would be trivial in normal life, a colleague's habit, a disagreement over a small decision, grow heavier when there is nowhere to go to recover from them. No walk around the block, no separate room that is truly separate, no social world outside the door to recharge against. By the final stretch, morale often recovers as the end goal comes back into focus. But the mid-mission dip is real, consistent, and documented across study after study. And this is for missions measured in weeks and months. A crewed round trip to Mars would last roughly 1.5 to 3 years, depending on the trajectory and the alignment of the planets. Not weeks, not a few months, years. Permanent settlements would involve people who may not return to Earth at all. The psychological demand of that is genuinely unprecedented. There is no historical analogue that maps cleanly onto it. And that matters, because when we reach for comparisons, the ones we find are less similar than they appear. Sailors once crossed oceans for months. Antarctic expeditions spent entire polar winters cut off from the rest of civilization. These are often offered as proof that humans can endure extreme isolation and come through it. The comparison contains truth, but it also obscures something important. Those people still had a sky. They could look out a porthole or a frosted window and see clouds moving, stars turning, a horizon that changed with the weather and the season. They felt wind. They experienced rain. They moved through a world that was hostile, yes, cold, yes, dangerous in its own ways, but recognizably a world. A natural world, with seasons and light, and the sense of being inside something larger than a metal container. That is not what space offers. On an airless world, nature is not indifferent. It is actively lethal. There is no sky to look at without a visor filtering radiation that would damage your eyes. There is no wind that does not carry abrasive dust or signal a pressure breach. There is no stepping outside for a moment of fresh air. Donning a spacesuit takes somewhere between 30 minutes and an hour. Every single time. The moment you finish that procedure and open the airlock, everything outside is trying to kill you by its ordinary existence. Not by storm, not by accident. Just by being what it is. Not isolated from civilization. Isolated from the natural world entirely. That is a different kind of confinement than anything sailors or polar explorers experienced. The psychological literature on analog environments was built on missions of weeks and months, conducted by crews who could at least look through a window and see a sky. What the mind does when even that is gone, across not months but years, we do not yet know with confidence. The honest answer is that we are at the edge of what the research has been able to test. The third quarter effect is documented and real. The isolation is documented and real. The nature as enemy condition is documented and real. But their combined weight across a mission measured in years, for people who may never return, is genuinely unprecedented. No crew has done it. No analog study has replicated it fully. The mind is a first-order survival factor on these missions. And what it will face at that scale remains an open question. And the Moon and Mars, as it turns out, do not impose that question equally. Here is where the comparison inverts. Everything covered so far has made Mars look like the kinder world. Its temperature is cold but consistent. Its dust is dangerous but less so than the Moon's. Its atmosphere does meaningful radiation work that the Moon cannot match. Its gravity, while insufficient, is more than 6 times stronger than the Moon's. In nearly every physical category, Mars offers a little more margin, a little more forgiveness. Then you consider the distance to Earth, and the scorecard reverses. The Moon sits roughly 384,000 kilometers away. At that distance, a radio signal takes about 1.3 seconds to make the trip one way. Round trip, 2.6 seconds. That is a barely noticeable pause. It is well within the range of a normal phone call, a normal conversation. From the Moon, you could call your family. You could hear their voices in something close to real time. You could argue with them, laugh with them, talk them through something difficult, and hear the response before you have forgotten what you said. The delay is there. You would notice it. But the conversation is real. And there is something else. From the lunar surface, Earth is not a distant dot. It is not a point of light in a black field. It is a vivid blue and white sphere, enormous in the sky, filling a portion of it that no planet from Earth ever manages. It is there every time you step outside. It hangs above you. It is your horizon decoration, your constant companion. The Apollo astronauts did not describe it neutrally. Edgar Mitchell, who walked on the Moon during Apollo 14, described a sudden, overwhelming sense of connectedness when he looked back at Earth from space. He called it a flash of understanding about the unity of everything. Dave Scott, who drove the lunar rover during Apollo 15, said Earth from the Moon was so beautiful, it was almost painful to look at. And it was William Anders, during Apollo 8 in December 1968, who pointed a camera out the window and took the photograph that would become known as Earthrise, a fragile blue bubble rising over the grey lunar surface. That single image helped ignite the modern environmental movement. It changed how a generation thought about the world they had come from. That image was taken by a human being looking out a window. From the surface, you would not need a camera. Earth would just be there. every day, above you. Now go to Mars. At closest approach, Mars is about 55 million kilometers from Earth. At its most distant, nearly 400 million kilometers. Across a typical crewed mission, the average distance is roughly 225 million kilometers. At those distances, radio signals take somewhere between 3 and 22 minutes one way. Round trip, between 6 and 44 minutes. There is no real-time conversation. There is no back and forth. You send a message, you wait, you get a reply, you wait again. More like a letter than a conversation. In a medical emergency, in a critical equipment failure, in any crisis where the next decision matters, mission control cannot help you in time. By the time Earth knows something is wrong, it may already be over. Whatever expertise is needed must already exist within your small crew. Whatever the right call is, you have to make it alone. On the moon, mission control watches every data feed live. Engineers can bark instructions the moment something looks wrong. That feedback loop, that constant presence of hundreds of people who know the system as well as you do, watching in real time, that is a form of safety that Mars removes entirely. And from the Martian surface, Earth is not a blue sphere. It is not even a distinguishable disk. It is a star, a bright point of light in the sky, one among thousands of other points, indistinguishable without a telescope. There is no visual anchor. There is no constant companion. There is just the dark. Research on communication delay has tried to capture what this does to a crew. Simulated Mars missions that introduced even modest artificial delays found that crew members reported increased feelings of autonomy. They also reported increased anxiety, decreased sense of safety, and greater reliance on their own internal group dynamics. That last point cuts in both directions. A crew with good dynamics, under the pressure of real autonomy, becomes tighter, more self-sufficient, more genuinely capable. A crew with poor dynamics, with no outside intervention possible in real time, lets conflicts escalate in ways mission control cannot reach. The delay does not just impose distance from Earth, it transfers psychological weight onto the crew itself, with no relief valve. The question of what happens when Earth disappears from the sky is one we do not fully know how to answer. Preliminary research drawing on analog studies and interviews with long-duration astronauts on the International Space Station suggests the experience could be qualitatively different from anything humans have faced before. Not homesickness, not loneliness in the familiar sense, something more fundamental, a kind of existential disconnection from every world you have ever known, hanging in a sky that no longer shows it to you. Some researchers believe that VR environments, curated media, and mission architecture that gives genuine autonomy and purpose could mitigate it. Others are less certain. The honest position is that we do not know. The closest analog we have is the Apollo blackout. When the command module passed behind the moon during a lunar orbit, it lost all communication with Earth for about 45 to 48 minutes at a time. Several astronauts described those minutes as among the most quietly powerful, utterly isolating experiences of the mission. Not frightening in an obvious way. Something stranger. A deep, complete silence. For 45 minutes. Now imagine that 45-minute wait every single time you try to reach a loved one. For 3 years. But the reality was different. Some researchers and explorers argue that radical distance might be freeing in ways that are hard to anticipate before you have experienced them. The Apollo astronauts did not merely survive psychologically. Many describe their time in space as the most profound and transformative experience of their lives. The overview effect, the shift in perspective that comes from seeing Earth from the outside, from grasping its smallness and fragility in a single glance, has been reported consistently across nationalities, backgrounds, and personalities. Genuine distance from the familiar can, under the right conditions, produce not despair, but clarity. Whether that holds over years rather than days, whether clarity sustains across the long middle of a mission where novelty has faded, and return is still far away, is the open question. We do not know. We should not pretend otherwise. There is one more twist, and it applies only to the moon. The moon is tidally locked. The same face always points toward Earth. That is why the near side, where the Apollo missions landed, always has Earth in the sky. But the far side never does. From the far side of the moon, you cannot see Earth. Not ever. And because the moon is close enough that the body of the moon itself blocks the line of sight, you cannot communicate directly with Earth either. China's Chang'e 4 mission, which landed on the far side in 2019, needed a dedicated relay satellite just to send and receive signals. That satellite is called Queqiao, which means magpie bridge, a name drawn from a Chinese myth about two separated lovers connected by a bridge of birds across the sky. It is a gentle name for a hard engineering problem. Any crewed base on the far side would face that same problem, compounded by human needs. The near side of the moon, with Earth always visible and a 2.6-second round-trip delay, might actually be psychologically easier than Mars despite greater physical dangers. The far side is scientifically extraordinary because Earth's radio noise cannot reach it there. A radio astronomer's dream of silence would present a psychological challenge that rivals or exceeds Mars on every dimension we have discussed. Step back from all of it for a moment. We are a species that evolved for one world. Our bodies, our minds, our social structures, our deepest needs, all of it shaped by Earth over millions of years. We are now seriously planning to send people to other worlds permanently, to raise children there, to build something that endures. The audacity of that should fill us with genuine awe. But doing it right means honestly assessing what those worlds demand, not the version of the demands that fits a hopeful narrative, the full version. And when you lay the moon and Mars side by side and ask which one a human being could survive longer, more fully, more completely, the answer is more complicated and more surprising than almost anyone expects going in. The physical categories favor Mars. The psychological categories, on the near side at least, favor the moon. And the far side is a world unto itself. The question of which hazard ultimately proves hardest to manage is still open. But the next layer of the comparison makes it stranger still. Add it all up. Every axis we have measured, every category we have examined. And the answer that emerges is not the one most people expect going in. The moon is closer. That much is obvious. 3 days by spacecraft, a radio signal that arrives in under 2 seconds. The Earth filling the sky above you like a lantern. You can speak to home and hear an answer before a sentence is finished. If something goes wrong, a rescue mission can reach you in days rather than years. These are genuine advantages, real ones, and they matter. But here is what the full accounting reveals. The moon is more immediately lethal than Mars across nearly every physical dimension we have examined. Its radiation environment is brutal, with doses up to 700 times the Earth's surface baseline and secondary radiation raising from the soil itself. Its temperature swings 300 degrees between sunlight and shadow, enough to destroy seals, crack materials, and degrade equipment across every thermal cycle. Its dust is chemically reactive, electrostatically charged, and shaped like microscopic razors that no filtration system has yet fully solved. Its gravity sits at 1/6 of Earth's, likely well below the threshold needed to keep a human body functioning over years and generations. And if something goes catastrophically wrong on the moon, a suit breach, a habitat failure, a cascade of small errors compounding into something unsurvivable, the nearest help is still 3 days away by spacecraft. Even if the decision to send it is made in seconds over the radio, proximity gives you a conversation. It does not give you a rescue. You cannot be saved by a phone call. Mars, by contrast, demands more. The journey is longer. The commitment is deeper. The communication delay stretches from minutes to the better part of an hour, depending on where the two planets sit in their orbits. Earth shrinks to a point of light, indistinguishable from 1,000 other stars. The psychological weight of that distance is real and documented, even if its full scale across multi-year missions remains genuinely untested. Mars asks more of the people who go there. And yet, the radiation dose on the Martian surface, measured directly by the Curiosity rover's instruments, comes in around 233 millisieverts per year. Serious, but meaningfully lower than the lunar surface, partly because the thin Martian atmosphere still filters some of what arrives from above, and partly because Mars soil can be piled over a habitat in ways the moon's naked surface makes far more difficult. The temperature swings on Mars are cold and consistent rather than violent and cycling. The dust is rounded rather than jagged, less chemically reactive, and its primary chemical hazard may be manageable in ways lunar silicate damage simply is not. The gravity at 38% of Earth's is more than 6 times stronger than the Moon's. Every day, across every body system, that gap accumulates. The evidence, taken together, radiation measurements, atmospheric modeling, dust chemistry, gravity calculations, points toward a conclusion that feels counterintuitive at first, and then, once you see it, feels almost obvious. For a permanent human presence, civilization rather than visitation, Mars offers a more forgiving starting point. The Moon is closer and more dangerous. Mars is farther and more forgiving. The solar system is full of such reversals. Proximity does not mean safety. Distance does not mean hostility. The relationship between nearness and survivability is not the one our instincts suggest. But this is where the comparison does something unexpected. Because the Moon's combination of danger and proximity is not simply a drawback. It is a specific kind of value. Think about what the Moon actually offers as a classroom. It is dangerous enough to be real. Radiation that can kill, dust that can destroy, materials under thermal stress, life support systems that cannot fail, power systems that cannot depend on regular resupply from Earth. Everything a Mars mission will face, the Moon forces you to solve. But while you are solving it, Earth is visible in the sky above you. Mission control can respond to a question before you finish the next sentence. And if the absolute worst happens, a spacecraft can reach you in days rather than years. The Moon is a test. Mars is the exam. Everything we need to learn before we commit people to a world years away from any conceivable rescue. We can learn on the Moon while the margin still exists. How to manage radiation across months and years. How to contain and filter dust through thousands of airlock cycles. How to extract water and oxygen from alien soil rather than carrying every molecule from Earth. How to build habitats and power systems and life support that do not depend on a resupply shipment arriving on schedule. How to keep people psychologically intact through long isolation with a small crew and no way out. All of it. The Moon is where we learn those lessons in the most unforgiving classroom in the solar system. And then, armed with that experience, the real experience, not the simulated version, we go to Mars. Which raises a question. If the Moon is this dangerous, this demanding, this lethal in ways most people have never appreciated, why are we going back? Not as a detour on the way to somewhere else. Not as a temporary staging post we intend to abandon. Why are nations and agencies and private companies converging on the Moon with serious long-term intent? The answer is not simply the proving ground logic, though that matters. The answer involves something found in the places the sun never reaches. The permanently shadowed craters at the Moon's poles, regions that have not seen direct sunlight in billions of years, hold water ice. Ancient ice, preserved in the cold and the dark, waiting. And water in space is not simply water. Engineers who work on deep space architecture have a phrase for it. They call water the oil of the solar system, the most strategic resource a world beyond Earth can offer. What that means, and why it changes everything about the Moon's role in humanity's future, is where this story goes next. The reason to return is not in spite of the Moon's deadly extremes. It is hidden in the coldest, darkest one of all. Near the Moon's poles, at the bottoms of certain craters, there are places the sun has never touched, not in recorded history, not since humans first looked up at the night sky, not in the entire 4.5 billion year history of the solar system. The floors of these craters have sat in permanent, absolute darkness since before the Earth had oceans. The physics behind this is straightforward. The Moon tilts only about 1.5 degrees on its axis. Earth tilts 23.5 degrees, which is why we have seasons, why summer days are long and winter days are short, why sunlight strikes the ground at changing angles across the year. The Moon has almost none of that tilt. Its poles receive sunlight at an angle so shallow, so nearly horizontal, that it barely grazes the surface. In deep polar craters, some dozens of kilometers wide and several kilometers deep, the walls rise too high and the angle is too low. Sunlight skims the crater rims and stops there. The floors remain untouched. They are sealed, as completely as if someone had closed a vault door billions of years ago and never returned. In that sealed darkness, temperatures fall to around minus 240 degrees Celsius. That is colder than the surface of Pluto. It is among the coldest confirmed places in the entire solar system. and something has been accumulating there, quietly, for billions of years. Water ice. Water has been arriving on the moon for as long as the solar system has been delivering it, carried by comets, asteroids, and water-rich meteorites striking the surface across geological time. When water hit the sunlit regions, it vaporized almost instantly. The moon has no atmosphere to hold it, so the vapor drifted away into space. But some of it migrated. Molecules wandering across the surface eventually found the polar shadows, where it is so cold that water in a vacuum cannot evaporate at all. It froze. It stayed. It accumulated, layer by layer, over billions of years, into deposits that scientists now believe could hold hundreds of millions of metric tons of water ice, perhaps more. A bone-dry world hiding an ocean's worth of frozen water in its darkest corners. The trail had been building for years. We had strong reason to suspect this for decades before we could prove it. In 1994, the Clementine spacecraft detected apparent signs of ice in permanently shadowed regions near the South Pole. Suggestive, but not definitive. In 1998, the lunar prospector found elevated concentrations of hydrogen near both poles. Hydrogen indicating water. Stronger evidence? Still not a confirmation. Then came 2009. NASA deliberately steered a spent Atlas V upper stage, the rocket that had carried the Lunar Reconnaissance Orbiter into space, directly into a permanently shadowed crater called Cabeus near the South Pole. The impact was calculated. A trailing spacecraft called L-Cross flew through the debris plume that billowed up into sunlight and measured what the crash had kicked loose. The instruments found water, not a trace, not an anomaly requiring interpretation. Water ice and water vapor in concentrations that removed all reasonable doubt. Definitively confirmed. Since then, the picture has only grown more striking. The Lunar Reconnaissance Orbiter mapped the poles in fine detail. India's Chandrayaan-1 spacecraft detected water molecules on the surface. NASA's SOFIA Observatory, an infrared telescope mounted inside a modified Boeing 747 aircraft that flies above most of Earth's atmosphere, detected water molecules even in sunlit regions of the lunar surface, suggesting water may be more widely distributed than the polar craters alone, possibly trapped in tiny glass beads created by ancient micrometeorite impacts. And in 2020, a set of studies published in Nature Astronomy significantly upgraded the total estimates of polar water ice. The moon is considerably wetter than the bone-dry world most people imagine. Now consider what water actually is. Water is 2 hydrogen atoms bonded to 1 oxygen atom. In the context of space exploration, that is not a chemistry lesson. That is a list of resources. Run an electrical current through water, a process called electrolysis, and it splits into hydrogen gas and oxygen gas. Oxygen to breathe. Hydrogen and oxygen together, chilled into liquid form, as liquid hydrogen and liquid oxygen, which is the most energetically efficient chemical rocket propellant combination known. The same propellant that powered the Space Shuttle main engines. The same propellant at the core of NASA's Space Launch System. So water ice on the moon is not 1 resource, it is 3. Drinking water, breathable oxygen, and rocket fuel, all derived from a single source, potentially manufactured on-site from what is already there. This is the idea behind in situ resource utilization, or ISRU. The phrase means using what you find where you are, rather than carrying everything from home. To understand why that matters, consider the numbers. Reaching low Earth orbit from Earth's surface requires a velocity change of roughly 8 kilometers per second. That is the energy cost of simply escaping the planet's gravity well. Getting from low Earth orbit down to the lunar surface costs roughly 6 kilometers per second more. But launching from the moon, with its gravity only 1/6 of Earth's, and no atmosphere to fight through, into lunar orbit or toward deep space, costs only about 2 kilometers per second. Not 6, not 8, 2. The moon is dramatically cheaper to launch from than Earth is. And the sunlit ridges just above the permanently shadowed polar craters, ridges that catch nearly continuous sunlight because of the moon's minimal axial tilt, could power solar arrays around the clock, providing the electricity needed to run electrolysis, splitting the ice below into propellant above. The vision that emerges from those numbers is a refueling depot, a gas station at the edge of Earth's gravity well. Spacecraft launching from Earth with minimal propellant, ascending to low Earth orbit on a fraction of what a traditional mission requires, then continuing to a lunar propellant depot where tanks are topped off with fuel, manufactured from ice mined in the crater shadows below. From there, onward to Mars, to the asteroid belt, to the outer solar system, at a fraction of the propellant budget a direct from Earth mission would demand. This cislunar propellant depot concept has moved from theoretical proposal to serious planning. Companies including United Launch Alliance have proposed exactly this architecture. NASA's Artemis program, beginning with Artemis Boom in 2022 and continuing with Artemis II as the first crewed flight beyond the magnetosphere since Apollo, is explicitly built around this longer ambition. Not a flag and a footprint and a departure, a sustained presence. An orbital station called the Lunar Gateway, a South Pole surface program targeting the one location on the Moon that has both confirmed water ice below and perpetual sunlight above. The ice itself may hold still more. The permanently shadowed regions likely contain not just water, but a broader collection of frozen volatiles. Carbon dioxide, ammonia, methane, other carbon and nitrogen-bearing molecules preserved in natural deep freeze vaults over billions of years. Carbon, nitrogen, hydrogen, oxygen. The four elements most critical to chemistry, to life, and to industrial production, sitting together in the coldest, darkest corners of our nearest neighbor. Step back and let that reframing settle. A world catalogued across multiple sections of this story as one of the most hostile environments imaginable, lethal radiation, violent thermal swings, chemically reactive dust, gravity too low to sustain a human body across a lifetime, also hides in its permanent shadows perhaps the most strategically valuable collection of resources in the inner solar system. The danger and the value come from the same place. The same axial tilt that eliminates seasons and leaves crater floors in eternal darkness also preserves the ice that darkness has been accumulating for billions of years. The same hostile extremes that make the Moon so difficult to inhabit are the reason the resources were never disturbed. The Moon is not a dead end. It may be the most important platform in the solar system, not for what it is to live on, but for what it enables as a waypoint. Exactly where the accessible ice deposits lie, how pure they are, how efficiently they can be extracted by machines or by crews, those questions remain genuinely open. Ground missions, robots, and eventually humans working in those permanent shadows will be needed to answer them. But the existence of the resource is no longer in doubt, and the strategic logic that follows from it is already reshaping every serious conversation about the future of human spaceflight. The oil of the solar system is buried in the Moon's most dangerous real estate, and reaching it may require solving every one of the hazards this story has been building toward. That strategic logic, the one already reshaping every serious conversation about human spaceflight, carries an immediate and genuinely contested question inside it. If the Moon is this valuable a platform, should we use it as the first destination? Should we go there before Mars? Or does going there first slow everything down? Serious people disagree, and the disagreement is not about enthusiasm or ambition. It is about strategy. One camp holds that the Moon is precisely the right first destination, not because it is an ideal place for permanent civilization, but because it is close enough to practice, close enough to iterate, close enough that when something fails, and something will fail, Earth is 3 days away by spacecraft, and about 1 second away by radio. The vision is to build infrastructure on the Moon, develop resource extraction technology, and learn to keep people alive in that brutal environment for extended periods. Solve radiation management there. Solve dust filtration there. Refine in situ water extraction. Test power generation, life support, and long-term habitat systems in a place where the cost of failure is not a 3-year catastrophe. Then push to Mars armed with everything learned, carrying propellant that the Moon itself helped produce. The Moon becomes a proving ground, a testing laboratory, a propellant depot, not the destination, but the apprenticeship. And here is what makes that argument genuinely striking. The Moon's very dangers, the ones this story has been building toward across radiation, temperature, dust, gravity, and psychology, are precisely what give the proving ground logic its force. Learning to manage those hazards in a place where resupply can reach you in days is a fundamentally different proposition from learning to manage them 8 months from Earth. If the lunar water extraction system fails, there is at least a framework for sending emergency supplies. If it fails on Mars, there is no framework. There is only the crew alone on a planet where the nearest help is months away in either direction. The moon's proximity is both its psychological comfort and its strategic advantage. Practice where you can afford to fail. Learn before the exam cannot be retaken. The other camp looks at that argument and calls it backwards. Elon Musk and SpaceX have been openly skeptical of the moon-first approach. Not quietly skeptical, openly. The argument from that side is that the moon is so environmentally different from Mars that what you learn there will not necessarily prepare you for what Mars demands. The resources and technologies developed for the lunar environment will not straightforwardly transfer. The geology is different. The atmospheric conditions are different. The dust is different. The gravity is different. And going to the moon first adds time and cost to a Mars program without proportionally accelerating it. The counter-argument says that learning on the moon is not learning for Mars. It is learning for the moon. The SpaceX vision centers on Starship, a fully reusable massive launch system designed to carry more than 100 people to Mars per flight. And on moving so fast, with so many missions, that sheer volume of activity accelerates the learning curve in a way a careful moon-first sequence never could. The logic is not slow and deliberate. It is iterative and aggressive. Fly. Learn. Fly again. Build the fleet. Build the city. The goal is not a Mars outpost. It is a self-sustaining Mars civilization, and the argument is that every year spent on the moon is a year not spent getting there. Both visions are serious. Both are actively funded and in development. Neither is a thought experiment. NASA, the European Space Agency, and JAXA, Japan's space agency, favor the more measured approach. The Artemis program and the Lunar Gateway, an orbital station planned for lunar orbit, reflect a coalition of international partners treating the moon as a genuine waypoint. Not flags and footprints, a sustained presence, a platform. The architecture assumes that what is learned and built at the moon will matter for what comes after. That the propellant depot concept is real. That the infrastructure investment is not wasted. So the debate is live, evenly matched, and not likely to be resolved by argument alone. The pattern only sharpens. The case for the moon as a proving ground grows stronger the more carefully you examine the moon's specific dangers. Not weaker. Stronger. Think about what the moon actually forces you to solve. Radiation shielding in an environment with no magnetosphere and no atmospheric buffer. Dust management for a substance that is chemically reactive, electrostatically charged, and abrasive at the microscopic level. Thermal engineering across a swing that exceeds 300 degrees. Water extraction from deposits buried in permanent shadow at temperatures approaching 240 degrees below 0 Celsius. Power generation and storage through 2-week-long nights. Long-duration psychological endurance in a confined, nature-deprived environment. All of these skills, developed on a world where Earth is a bright blue sphere filling the sky, and radio signals take about 1 second to arrive, are skills that Mars will require. Not similar skills, the same skills, in a more forgiving classroom. The paradox at the heart of the debate is one that does not fully resolve in either direction. The moon is closer and more dangerous. Mars is farther and more forgiving. The moon's surface environment is in several measurable ways more immediately lethal, and yet the moon's proximity is what makes its lethality manageable as a learning environment. You can practice there in a way you cannot practice on Mars, precisely because the moon offers no forgiveness in its physical conditions and substantial forgiveness in its rescue logistics. Not a friendly proving ground, the hardest nearby school there is, but nearby. Whether lunar lessons and technology transfer cleanly to Mars is genuinely contested. Whether the moon-first sequence accelerates a Mars program or delays, it is genuinely contested. Engineers, scientists, astronauts, and policymakers are having that argument in real time, with real funding, real rockets, and real mission architectures on the table. What is not contested is what the debate reveals about how seriously the question is now being taken. The era of treating Mars as a distant aspiration and the moon as a nostalgic footnote is over. Both worlds are back in play, as destinations as waypoints, as strategic choices with generational consequences. And the argument over which to go to first may ultimately be decided not by philosophy, but by which architecture succeeds, which system reaches orbit reliably, which extraction technology actually works in those permanent shadows. The debate itself is new. The scale of the ambition behind both sides of it is new. And whichever path proves correct, the hazards waiting on both worlds are the same ones this story has been laying out. The Moon and Mars both demand answers to questions humanity has never had to answer before. The question of sequence, Moon first or Mars first, may be the next great argument in the history of exploration, and it is already underway. But before we argue about where the Moon fits in our future, it is worth remembering something more fundamental. The Moon is the reason we have a future at all, not in any poetic or approximate sense, in a precise scientific one. The Moon did not always exist. It was not always there, hanging in the sky, pulling the tides, making the nights bearable. It was born, and the way it was born is one of the most violent events in the history of the solar system, a collision so total, so catastrophic, that calling it an impact feels inadequate. To understand it, you have to go back, not decades, not centuries, about 4.5 billion years. The solar system in those early days would be unrecognizable to us. The sun had just ignited, a new star burning through its infant instability. Around it spun a vast disk of gas and dust, everything slowly drawing together under gravity. Rocky bodies formed, grew, swept up more material, collided with other growing bodies. The inner solar system was a demolition derby on a planetary scale. Impacts were not rare catastrophes. They were the process, the very mechanism by which planets are made. Rock crashing into rock, heat melting stone, bodies merging and reforming and merging again. Earth was already there, already most of its final size. But it was not the Earth we know. Its surface was not solid ground. It was liquid, oceans of molten rock, rolling and churning under a sky filled with debris. Deep inside, heavy iron and nickel were sinking toward the core, separating from the lighter, silicate rock around them. In broad outline, you could recognize it as the future home of everything you have ever known. In detail, it was alien, and sharing a similar orbit around the young sun was another body. Scientists named it Theia, for the Greek titan who was mother to Selene, goddess of the moon. A fitting name. Theia was roughly Mars-sized, a substantial planetary body in its own right, growing alongside Earth, its gravity and Earth's gravity tugging at each other across their shared orbital path. For millions of years, this relationship was stable enough. Then it wasn't. The gravitational balance shifted. The two bodies drifted toward each other, and the inevitable arrived. Theia hit Earth. Not a glancing blow, not a near miss. A direct, oblique collision between two planetary bodies, each carrying millions of years of accumulated mass and momentum. The energy released was not the kind that can be pictured easily. The outer layers of both worlds vaporized. Rock did not melt. It became plasma, the fourth state of matter, beyond liquid, beyond gas, a superheated cloud of particles that had been solid continents moments before. Vaporized silicate, shattered protoplanet fragments, molten rock. All of it was hurled outward in an enormous cloud, thrown into orbit around what remained. Most of Theia's mass was absorbed into the reformed Earth. The two bodies merged, but a portion of that ejected debris stayed in orbit. It did not fall back. It stayed. And then that debris did something remarkable. Over a timescale, scientists estimate at somewhere between a few decades and a few thousand years, extraordinarily fast by any geological measure, that orbiting cloud of shattered rock began to draw back together. Gravity pulled the pieces toward each other. They collided, merged, compacted, cooled. The cloud of debris rounded itself into a sphere, and the sphere became the moon. Here is what makes this more than just a spectacular origin story. In the 1980s, planetary scientists William Hartmann and Donald Davis formally proposed what is now called the giant impact hypothesis. A Mars-sized body colliding with the early Earth, debris thrown into orbit, rapid reassembly into a new world. The idea was bold. At the time, it was contested. The evidence that followed was not. When Apollo astronauts brought lunar rocks back to Earth, Scientists analyze them. Not just their mineral composition, but their isotopic ratios, the precise ratios of different atomic variants of the same element: oxygen, titanium, tungsten, silicon. These ratios act like fingerprints. Every body in the solar system that formed independently has slightly different ratios, shaped by where in the disk it formed, what material it swept up, how it cooled. The moon's isotopic fingerprint does not match an independent origin. It does not match a captured body. It matches Earth's mantle. The match is striking, far closer than chance, far closer than any model of independent formation predicts. The lunar rocks the Apollo crews collected are, in the most literal sense, made of Earth. Not rocks that resemble Earth's rocks. Not rocks that share a distant ancestor. Rocks that were once part of this planet's own outer layers, vaporized, thrown into space, cooled, and reassembled into a new world 40,000 kilometers overhead. The moon is Earth, rearranged. The giant impact hypothesis is still a hypothesis, as science rightly insists. Details of the collision's exact angle and energy are still being refined. Competing models exist, but the isotopic evidence from Apollo's returned samples is not easily explained away. It points, firmly and repeatedly, in one direction. Theia hit Earth, the debris reassembled, and the world that formed from that catastrophe has been orbiting us ever since. Think about what that means. The object that has governed our tides, steadied our axis, lit our nights, inspired our calendars, pulled our oceans into rhythms that may have been critical to the first chemistry of life. That object is not a visitor, not a capture, not a coincidence. It is a piece of this planet returned to us in a different form, circling at a distance of roughly 1 light second, as it has for most of Earth's history. The violence of the birth is almost impossible to hold in the mind. A Mars-sized planet, a world vapor flash, a solar system 4.5 billion years into its own formation. And from that disaster, a companion. From that annihilation, the conditions for everything that followed. That consequence is where this story is heading next. That consequence is not abstract. It is not a side note to the collision story. It is the reason the collision story matters at all. The giant impact did not just make a moon, it quietly set the conditions that would, 4 billion years later, make you. Start with something simple. Earth tilts. The planet's rotational axis is not straight up and down relative to its orbital path around the sun. It leans at an angle of roughly 23.5 degrees. That lean is why we have seasons. When the northern hemisphere tilts toward the sun, it receives more direct light for more hours each day. Summer. When it tilts away, the opposite. Winter. The same rhythm runs in the southern hemisphere, reversed. Those seasons have shaped the evolution of life for hundreds of millions of years. The great migrations of animal species, the advance and retreat of glaciers, the cycling of nutrients through soil and ocean, the flowering of plants in spring and their retreat in autumn, all of it flows downstream from that 23.5 degree lean. Seasons are not a pleasant backdrop to life's history. They are one of the engines driving it. But something was wrong. That tilt is not stable on its own. Run a computer simulation of the solar system and remove the moon. Watch what happens to Earth's axial tilt over millions of years. It does not stay near 23.5 degrees. It wanders. The gravitational tugs of the other planets, Jupiter pulling from the outer solar system, the subtle accumulated effects of orbital mechanics acting over geological time. These forces would push Earth's tilt into regions it cannot currently reach. Simulations show the tilt swinging chaotically, from near 0 degrees to over 80 degrees, with no stable resting point and no predictable cycle. Just drift. Just chaos. Think about what 80 degrees means. A planet tilted that severely essentially rolls on its side. The poles no longer trace a gentle arc through partial sunlight across the year. One pole faces the sun directly for roughly half the year, baking in continuous light, then darkness for the other half. Climate does not shift gradually with that geometry. It swings violently, season to season, year to year, across millions of years of geological time. The kind of slow, patient evolutionary refinement that eventually produced complex life, that took hundreds of millions of years of incremental adaptation in broadly consistent environments might never have found stable ground to work from. Not delayed, not slowed, never started. The moon prevents this. Its gravitational influence as a large nearby body acts as a gyroscopic anchor on Earth's tilt. It keeps that angle in a narrow range over geological time, stable enough for predictable seasons, stable enough for persistent ecosystems, stable enough for evolution to proceed along consistent lines across the vast spans of time complex life requires. Without the moon, there may have been no stable Earth. Without a stable Earth, no us. The moon is not a passive companion. It never has been. Its gravity does something else. It pulls on Earth's oceans and slightly on the solid rock of the crust itself, creating a tidal bulge that sweeps around the planet as Earth rotates. The sun contributes to the tides as well, but the moon's tidal effect is roughly 2.5 times stronger than the sun's, despite the sun's incomparably greater mass. The reason is distance. Tidal force depends on how sharply gravity changes across the span of an object, and the moon is so much closer that its gradient across Earth's diameter dominates. The sun is vastly more massive. The moon simply wins because it is nearby. Those tides have been running for 4 billion years, and over that time they have done something remarkable to the Earth-Moon system. Every tidal cycle transfers a small amount of angular momentum from Earth's rotation outward to the moon's orbit. Earth's spin slows imperceptibly slowly, year by year. The moon drifts outward. Today, the moon recedes from Earth at about 3.8 centimeters per year. We know this with extraordinary precision, not from theory, but from measurement. Apollo astronauts left retroreflectors on the lunar surface, small arrays of mirrored prisms that reflect laser pulses directly back to their source. For decades, observatories on Earth have fired laser pulses at those retroreflectors and timed the returning light. The distance has been tracked with centimeter accuracy, year after year. The moon is leaving. Slowly, measurably, verifiably. Run that same measurement backward through time, and the picture changes dramatically. About 4 billion years ago, the moon was perhaps 10 times closer to Earth than it is today. Earth rotated far faster. A day may have been only about 6 hours long, and the moon hanging that close in the sky would have raised tides of staggering scale. Not the gentle coastal rhythms we know. Something closer to geological forces acting on the ocean itself, moving vast quantities of water with every short rotation of the faster spinning planet. Those enormous early tides may have done something critical for life. This is where the story gets genuinely surprising. Tidal mixing driven by the moon would have continuously stirred the early ocean, cycling nutrients from the seafloor toward the surface, bringing minerals into contact with organic molecules, and creating the rich, energetic environments at coastlines and tidal pools where chemistry and biology could meet. Tidal pools, those sheltered pockets of seawater periodically exposed and submerged by the tides, remain among the most chemically productive environments on Earth. Intense concentration of molecules, repeated wetting and drying, energy input from sunlight and from tidal motion. Many scientists believe the earliest life may have taken its first steps in exactly these environments. The moon didn't just stabilize Earth's climate, it may have helped stir the primordial soup. Not a coincidence, not a minor contribution, potentially a prerequisite. The connection runs deeper still, though here the science moves into territory still being actively mapped. Earth's core generates the magnetic field that shields the surface from solar wind and cosmic radiation. That field depends on churning liquid iron in the outer core, driven by heat from radioactive decay and by energy released as the inner core slowly solidifies over geological time. Some researchers have proposed that the giant impact itself helped structure Earth's interior in ways that contributed to the field's long-term strength and persistence. The collision rearranged the deep interior of a planet, and that rearrangement may have had consequences for the core and the dynamo it drives. This remains an active research area. We do not fully understand it yet. What is not debated is the result. Earth's magnetic field is unusually strong and has been unusually persistent. Mars lost its global magnetic field roughly 4 billion years ago. Its smaller core cooled too quickly, the churning stopped, and the dynamo failed. Without a field, The solar wind stripped away Mars's thick early atmosphere over hundreds of millions of years, turning a world that may once have had liquid water on its surface into the cold, thin-air desert it is today. Venus, roughly Earth's size, rotates so slowly that its interior generates only a negligible field. Earth's field has persisted for billions of years, quietly doing the work of shielding every living thing on its surface from radiation that would otherwise be lethal. That shield may be partly a legacy of what the moon's formation set in motion inside the planet that made it. The moon is woven into Earth's story at every level, the tilt that gave life predictable seasons, the anchor that kept that tilt from swinging into chaos, the tides that may have stirred the earliest chemistry of life into existence, the possible interior consequences that helped sustain the magnetic field that kept the atmosphere in place. Pull the moon out of the picture, and the consequences cascade. The story of life on Earth may not be separable from the story of a collision 4.5 billion years ago. And the moon's role in what comes next, in what humanity is now choosing to do with it, is a different kind of consequence entirely. Follow that chain of consequences to its very end, and it arrives somewhere unexpected. It arrives at you. Every atom in your body has a history. The carbon woven through your DNA was forged in the core of a star that lived and died before the solar system existed. That star ran out of fuel, collapsed, and exploded with enough force to scatter its interior across light years of space. The iron in your blood came from a similar death. Not ordinary stellar burning, but a supernova. A detonation so energetic that it produced elements heavier than anything ordinary fusion can build. Your calcium, your phosphorus, your oxygen, all of it stardust, all of it carried here by cosmic violence, billions of years old. You are, in a literal and measurable sense, the recycled debris of dying stars. But here is where it gets strange. The specific configuration of those atoms that makes you a conscious, wondering, questioning human being does not just depend on stellar deaths. It depends on a sequence of events that includes the moon. Follow the chain. Without the giant impact 4 billion years ago, no moon forms. Without the moon, Earth's axial tilt wanders without a stabilizing anchor, drifting from near 0 degrees to over 80 degrees. Without a stable tilt, consistent seasons collapse. Without consistent seasons, and the long, predictable ecological rhythms they produce, complex life may never gain the foothold it needs. Without complex life, no nervous system evolves capable of consciousness. Without consciousness, no one looks up at the sky and wonders about any of it. You exist in part because a Mars-sized planet crashed into the young Earth 4 billion years ago, not as poetry, not as metaphor, as a chain of physical consequences, each one following from the last. The moon has been present for all of it. It is older than the oceans in their current form, older than the continents as we know them. It watched from the sky as life crawled from the sea onto barren rock. It watched as plants colonized the land, as insects took to the air, as enormous animals ruled the surface for 150 million years and then perished in a single catastrophic moment. It watched as small, warm-blooded mammals crept out from the shadows and slowly, over tens of millions of years, stood upright. And eventually one of those upright creatures looked up at the moon and began to ask questions. The moon has been watching the entire time. Now hold that image next to the other one. The moon that will bombard an unprotected astronaut with radiation at 700 times the Earth's surface dose. The moon whose dust particles are microscopic razors, chemically reactive and never worn smooth. The moon whose surface temperature swings 300 degrees between sunlight and shadow. The moon that has no atmosphere to soften any of it. That moon, this one. Same object. Not a distant hazard and a friendly companion. The same world. Simultaneously, our most dangerous nearby destination and the closest cosmic companion we have. The world most likely to kill an unprepared visitor, and the world most responsible for creating the conditions under which any human being exists at all. That is not a contradiction that resolves neatly. It simply is. The same oblique impact that scattered debris into orbit, that reassembled into the moon over decades or centuries, that locked the moon into its rhythmic gravitational relationship with Earth, also set in motion the sequence that produced you. And the world produced by that impact will, if you step onto it without adequate preparation, kill you. That companion is exactly where we are now going back. In 2024, 4 astronauts climbed aboard an Orion spacecraft and traveled farther from Earth than any human being had ventured in more than 50 years. Reed Wiseman, Victor Glover, Christina Koch, and Canadian astronaut Jeremy Hansen flew around the moon and returned. Artemis II, the first crewed mission to travel beyond Earth's magnetosphere since Apollo 17 left the lunar surface in December 1972. Think about what that gap means. 52 years, 2 generations, the entire span of time from the last Apollo footstep to the moment Artemis II slipped past the boundary of Earth's magnetic shield and entered the radiation environment that this video has spent considerable time describing. They went, they came back, and the missions that follow are aimed at a specific destination on the lunar surface, the South Pole, near the permanently shadowed craters where water ice has been confirmed waiting in the cold and the dark. But here is the part that looks familiar and is not. Going back to the moon in the Apollo era meant flags, footprints, and samples. Going back now means something categorically different. It means learning how to survive, how to extract water from frozen regolith and split it into drinking water, breathable oxygen, and rocket propellant. How to shield human bodies from radiation in an environment where the hazard is continuous and partly unsolved. How to manage dust that grinds into every joint and seal and infiltrates every airlock, every day, without exception. How to keep minds stable and functional in confinement that exceeds anything in prior human experience. These are not side problems. They are the curriculum. The moon is the hardest nearby school we have. And what we are attempting now with Artemis, with the South Pole program, with every instrument and prototype and habitat design currently being tested, is to graduate from it before taking on what comes next. What comes next is a journey of roughly 225 million kilometers. That distance is not the moon at 1 light second. The world at the end of that journey has a thin carbon dioxide atmosphere that provides almost no protection. Iron oxide deserts stretching in every direction, the largest volcano in the solar system, and canyon systems that make the Grand Canyon look like a crack in the sidewalk. The transit to reach it takes roughly 8 months. The crew that will make that transit will number around 6 people, confined to a spacecraft the size of a modest apartment, watching the radiation counter climb every single day of that journey. And once they arrive, the question that every Mars mission planner confronts becomes unavoidable. The dust, the radiation, the gravity, the isolation, the communication delay, the thin air that cannot be breathed and barely slows a spacecraft entering at hypersonic speed, all of it at once. All of it with no resupply possible, no rescue reachable, and no margin for the kinds of failures that Earth-based missions absorb routinely. The moon is where we learn whether we can handle any of that. It is close enough that failures are survivable, recoverable, instructive. Mars is not. And that is precisely why the moon, the world made of Earth's own shattered surface, the world that stabilized life's conditions for billions of years, the world that would kill you if you stepped onto it unprepared, is also the world that may determine whether humans ever reach the one beyond it. The next question is what that journey actually looks like. Not the mission graphics. The reality of 8 months in transit, the entry into a Martian atmosphere simultaneously too thick to ignore and too thin to rely on, the first moments of standing on another planet, and the problem that waits at the end of a successful landing. How do you get people back? The reality begins the moment you leave, not the launch, not the press conferences or the years of preparation. The reality begins when Earth is behind you and there is nowhere else to go. You're in a spacecraft roughly the size of a modest apartment. There are 5 other people. The walls do not change. The view does not change. The recycled air tastes the same every morning, and it will taste the same for the next 8 months. Behind you, Earth shrinks a little more with every hour. Not dramatically, not all at once, just steadily, day by day, until it becomes something you check through a porthole rather than something you feel beneath your feet. Ahead of you, there is nothing visible yet, just stars, just the blackness of interplanetary space, and somewhere roughly 225 million kilometers away, a rust-colored dot you will not see with the naked eye for weeks. The radiation counter on the panel ticks upward every day. Galactic cosmic rays and solar particle events, the same particles discussed in mission briefings for years, are now accumulating in your tissues in real time. Nothing you can feel, nothing you can see, but the number climbs. The food is rationed with a precision that leaves little room for appetite or preference. The water you drink today is the water you breathed out yesterday, recovered, filtered, and recirculate through systems that cannot be allowed to fail. Your bones are losing density, your muscles are losing mass, your cardiovascular system is slowly forgetting what it feels like to push blood upward against a full gravitational field. And the communication delay is growing. In the early weeks, Earth's voice arrives with a lag of a few minutes. Manageable, disconcerting, but manageable. By the time you're deep into the transit, the lag has grown to tens of minutes each way. A question sent to mission control waits half an hour for an answer. A conversation becomes something else entirely. More like a letter than a conversation. You say what you need to say, you wait, and eventually something comes back. The people on the other end are still there. They are just very, very far away. 8 months of this. That is the reality, not the mission graphics. Then you arrive. The picture was not what it seemed. Because arriving at Mars is not a triumphant entry. It is not a moment of triumph at all. It is 7 minutes of complete silence, total autonomy, and no margin for error. Entry into the Martian atmosphere is one of the most technically demanding maneuvers in the history of spaceflight. The spacecraft hits the top of the atmosphere at interplanetary cruise velocity, and for approximately 7 minutes, it is wrapped in superheated plasma generated by the friction of deceleration. Communications are blacked out, no signal gets through the plasma sheath, no command can be sent from Earth, no intervention is possible from mission control. Every system must work perfectly, in the correct sequence, executing a choreography it rehearsed in simulations but has never performed in the actual Martian environment. And here is the part that sharpens that further. By the time mission control even knows the entry has begun, it is already over. The signal confirming the start of entry travels across hundreds of millions of kilometers at the speed of light and arrives on Earth long after the spacecraft has either landed or not. The crew is on their own, entirely. Mars's atmosphere makes this harder in both directions at once. It is thin enough to provide only modest deceleration. It cannot slow a large crewed spacecraft, the way Earth's thick atmosphere slows a returning capsule, but it is thick enough that you cannot ignore it. You must use it precisely, combining atmospheric drag with retro rockets and possibly large parachutes in a carefully timed sequence that must execute flawlessly after 8 months of exposure to launch vibration, solar radiation, and the cold of deep space. NASA's robotic landers have done this. Curiosity, weighing roughly 900 kilograms, used a sky crane system, a hovering rocket-powered descent stage that lowered the rover on cables to the surface. Perseverance used the same approach. Both worked. Both were engineering achievements of the highest order. But a crewed Mars spacecraft is not 900 kilograms. It is orders of magnitude heavier. Life support, return propellant, food, water, and equipment for a stay of potentially 500 days or more add up to a mass the sky crane architecture simply cannot lift. The approach that worked for robots does not scale to people. SpaceX's Starship is designed to solve this by landing propulsively, using rocket engines to decelerate all the way to the surface with no parachutes and no cranes. It is the most serious current attempt to close that engineering gap. Whether it can deliver at the scale a crewed mission requires remains to be demonstrated. The effort is real. The solution is not yet proven. Say you land. Say the hatches hold and the habitat inflates and the power comes online. You move through the checklist and then through the airlock, and then you step onto another planet. What you see is not what any photograph prepared you for. The sky is not black. It is not blue. It is pale butterscotch, shading to pinkish tan at the horizon, with a faint muted blue around the sun where fine dust scatters light in ways no Earth atmosphere produces. The ground is iron oxide red, rock and sand in every direction, stretching to a horizon that sits slightly closer than Earth's, because Mars is a smaller world. Gravity pulls at roughly 38% of what you have known your entire life. Not weightless, noticeably lighter. Your suit and equipment absorb much of that difference in practical terms, but the body notices. The air pressure outside is under 1% of Earth's, unsurvivable without the suit, immediately and completely. But that thin atmospheric buffer, the same air that is barely enough to cause problems during entry, provides meaningful shielding from the radiation environment that the open surface of the moon cannot match. The planet itself offers a layer of protection the moon never will. And the scale of Mars, which is easy to underestimate from the data, becomes visceral when you look at it. Olympus Mons, the largest volcano in the solar system, rises roughly 22 kilometers above the surrounding plain. That is nearly 2.5 times the height of Everest. Valles Marineris, the canyon system visible from orbit, stretches nearly 4,000 kilometers end to end, long enough to span the continental United States. These are not features. They are geological facts that redefine the word large. The temperatures here demand respect. At the equator, in direct midday sunlight, the surface might briefly reach 15 or 20 degrees Celsius, something approaching livable. By nightfall, the same location drops to minus 70 degrees or colder. The poles in winter reach minus 125 degrees. The planet-wide average hovers around minus 60 degrees. Cold, relentlessly cold, but cold in a consistent, insulated against way that the moon's 300-degree swings across a single day never permit. Dust storms are a real operational concern. A regional storm is routine. A global storm, one that can darken the sky for weeks or months, and cut solar power to a fraction of its normal output, is not common, but not rare either. Backup power for a crewed Mars base would almost certainly need to be nuclear. Small fission reactors or radioisotope thermoelectric generators that produce heat and electricity independent of sunlight. The perchlorates in the Martian soil, chlorine-bearing salts that are toxic to the thyroid, require careful management to keep them out of the food supply, the water, and the air. And radiation, while meaningfully reduced from what the open moon delivers, still accumulates over a 500-day surface stay. By the end of a long Mars mission, a crew would be approaching the career dose limits currently used for astronauts. None of it is easy. None of it is safe by any standard the phrase safe normally implies. And yet all of it, taken together, points toward a conclusion that surprises most people who have followed the hazards closely. Mars is more survivable, not comfortable, not forgiving, not easy, but more survivable for long-duration human presence than the moon, as the moon actually exists today. The radiation is less severe. The temperature swings are smaller and more manageable. The dust is rounded by ancient wind and water rather than sharpened by billions of years of micrometeorite impact. Less abrasive, less chemically hungry, less likely to destroy equipment and lungs at the same rate. The gravity, at 38%, is more than 6 times the moon's, and while it is not enough to fully protect bone and muscle over the long term, it is enough to make a meaningful physiological difference. The thin atmosphere filters particles the moon's non-existent atmosphere cannot touch. The planet itself provides radiation shielding from the ground and the sky in ways no lunar surface ever will. If something goes wrong on Mars, you are months from any possible help. That is a terrifying fact. But you're also working with more atmospheric buffer, more gravity, more in situ resources, more of the raw material that long-duration human survival requires. The moon will kill you faster, in more ways, with less warning. Mars demands more from your ingenuity, your resilience, and your willingness to accept permanent distance from everything you have ever known. But the planet itself is the more forgiving host. This is what the moon is for. Not the destination. The school. The moon is a test. Mars is the exam. We go back to the moon to learn how to extract water from frozen crater floors, how to shield habitats against galactic cosmic rays, how to manage dust that never stops accumulating, how to build power systems that do not depend on continuous resupply from Earth, how to sustain the psychological health of a small crew through isolation and confinement, and the slow erosion of the familiar. We learn all of that while Earth is still visible overhead, while a rescue mission is days away rather than years, while the cost of a catastrophic failure is survivable at the level of the program, if not always at the level of the crew. Then we go to Mars armed with what we learned, not because Mars is easy, because it is, of all the places within reach, the most realistic long-term home our species has ever had access to. A day on Mars lasts 24 hours and 37 minutes, nearly identical to Earth's. The poles hold water ice in quantities large enough to sustain a permanent presence. The thin atmosphere, while unbreathable now, is real enough that some researchers have proposed that over geological timescales, it could in principle be thickened via terraforming, though that is firmly in the realm of the distant future. Not a plan, but a possibility that the physics does not forbid. The gravity, while insufficient by Earth standards, is enough to give the body something to work against in ways the Moon never offers. Mars is not Earth. It will never be Earth, but it is the world most amenable to the long, patient, enormously difficult project of becoming somewhere humans can not only survive, but, over generations, thrive. We began this by asking why the Moon would kill you before Mars could. The answer turned out to be richer than the question. The Moon's dangers are real and often more immediate than Mars's in every category we examined. And yet the Moon is also the world born from Earth's own catastrophe. The world that steadied our axial tilt and kept our climate stable long enough for complex life to emerge. The world that stirred the ancient oceans, that watched over all of human history from the beginning, that gave us Apollo and gave us wonder, and gives us now the most unforgiving classroom in the solar system. Its extremes are the same extremes that preserved billions of tons of water ice in its darkest craters. Its dangers are the curriculum. Beyond it, Mars waits. Farther, colder, more isolated, more demanding, and more inviting than anywhere else within reach. One day, if we do the work, a human being will stand on the Martian surface and look up at the night sky. They will find a bright point of light among thousands of others. Not a world filling the sky the way Earth fills the lunar sky. Not a place that feels like home in any immediate sense. A pale blue dot. One point of light among many, indistinguishable without knowing where to look. And they will know they're standing on another planet. That the species that built fires and carved stone and looked up at the Moon for 10,000 years before walking on it has, for the first time in its history, made a home somewhere else. Not as a metaphor, not as a symbol, as a physical fact. That is not science fiction. It is science in progress, happening now in laboratories and launch pads and mission planning rooms and research stations, carried forward by thousands of people who decided that the right response to the universe's immensity is not fear, but curiosity. Not retreat, but exploration. The Moon wants to kill you. Mars is a little more patient about it. But the universe, vast and ancient and indifferent and breathtakingly beautiful, is out there. And we are going.